Okay, this is 2007 for response number 3, and it says here, an external direct current power supply is connected to 2 platinum electrodes immersed in a beaker containing 1 molar CuSO4 at 25 degrees Celsius, as shown in the diagram above. As the cell operates, copper metal is deposited onto one electrode and O2 gas is produced at the other electrode. The two reduction half reactions for the overall reaction that occurs in the cell are shown in the table below. Here. So the first question it asks us is, on the diagram, indicate the direction of the electron flow in the wire. So here, to find the direction of electron flow, we have to look at the half reactions. Now, because this is an electrolytic cell, and not a galvanic cell, because it only has one chamber as opposed to 2. The most positive one, which is this one, is going to be flipped and oxidized instead of reduced. And then this one will end up being reduced. So because this is oxidized, we look up here, and the O2 gas here is on this electrode. So this electrode is being oxidized, and because of because of NOx, this is the anode. And because of red cat, this is the cathode, because it's being reduced. Now, this makes sense because the gas that's coming out of this electrode is making this electrode smaller, and then the Cu solid is making this electrode bigger. So because the anode will always get smaller and the cathode will always be bigger, so the electron flow will go from the anode to the cathode. So we write down anode to cathode, which is right to left. And it will always flow from the anode to the cathode. It's just finding out which one is the anode and which one is the cathode. Next, it asks us, write a balanced net ionic equation for the electrolysis reaction that occurs in the cell. So to write this equation, we have to look at the first 2 parts of it. So here, this equation is staying the same way in order. So we know that Cu plus 2 is the first part. And then here, this equation is going to be flipped, so H2O is the first part. Now we have to look at the electrons, and we see that this equation has 4 electrons, and this one has 2. So we have to multiply this equation by 2 in order to have the electrons be the same. So now we write our equation, which will be 2H2O plus 2Cu plus 2, because we doubled it. And then we see that the products are here, Cu and O2, and H plus because of the H2O. And then we balance it, so we have 2 Cu, 2 O2, and 2 H plus. And we have 4 electrons overall. So that's our balanced net ionic equation. Now the next question is, predict the algebraic sign of delta G for the reaction and justify your prediction. So we can tell what the if delta G is positive or negative by seeing if the reaction is spontaneous or not spontaneous, and we can find that by looking at E. Now we see that if we add, this is going to be negative 1.23, so if we add 0.34 to negative 1.23, that's still going to be negative. And whenever E is negative, the reaction is not spontaneous. And because the reaction is not spontaneous, delta G is positive. Okay. Next question it asks is, calculate the value of delta G for the reaction. So first we have to find out what the exact number for E is. So E equals negative 1.23 plus 0.34, and that will equal negative 0.89. E is in volts, and volts it equals joules over coulombs, which is just something that you need to know. And then we plug this number into our equation to find G, which is delta G equals -n, which n being the number of electrons, F, which is Faraday's constant, which is going to be Q coulombs over moles of electrons, and then E, which is the number we have here. So then we plug that in. So -4, which is what we found in our reaction up here. -4 times Faraday's constant, which is 96,500 coulombs per mole. And then -0.89, which is all, it's kind of tight there, but it's -0.89 joules per mole, or column, sorry. -0.89 joules per column. And then we find that the columns cancel out, and then we're left with joules over moles. And once we plug this into a calculator, we find 340,000 joules per mole. Because this is in joules and we want it in kilojoules, it's going to end up being 340 kilojoules per mole. So that's our number for delta G. Next, it asks us to find, it tells us that an electric current of 1.5 amps passes through the cell for 40 minutes. So amps here, we know that amps, or charge, equals coulombs per second. So knowing that, we know that we're going to use this and use coulombs and Faraday's constant to end up finding the mass here, which has to calculate the mass in grams for Cu solid that is deposited on the electrode. So we're going to find mass using Faraday's constant, which is grams over moles of electrons, and then we'll use those moles to find the mass. So 1.5 amps, which is coulombs per second, for 1 second, by 40 minutes, just times, and then we times that by, because we want to cancel out the minutes and the seconds, we go 60 seconds per 1 minute. So seconds cancel out and minutes cancel out, and then we only have coulombs. And if we plug that in, we see we have 0.00936 coulombs. Oh, whoops, sorry. We have 3,600 coulombs. So now that we have the columns, we can use stoichiometry to find the mass of Cu. So we have the columns here, and then we know that 96,500 coulombs per 1 mole of electrons is Faraday's constant. And for every 2 moles of electrons, which we can see by looking up at this half reaction, every 2 moles gives us 1 mole of Cu. So for every 2 moles of electrons, we have 1 mole Cu. And then for every 1 mole of Cu, we have 63.55 grams, which we can find by looking at a periodic table. And then if we plug that in, we'll find that it equals 1.19 grams of Cu. So that's our mass of Cu. And now it's asking us to calculate the dry volume in liters measured at 25 degrees Celsius and 1.16 atm of the O2 that is produced. So I see that it has temperature and pressure, and it wants us to find volume. And the way I know how to do that is using gas laws. And in order to make the ideal gas law equal volume, it will be V equals nRT over P. And the only problem is finding the moles of O2. But by using the grams of Cu, we can find those moles. So the first thing we're going to do is convert 1.19 grams of Cu into moles of O2. So for every 63.55 grams of Cu is 1 mole. And when we look at the overall reaction, with every 2 moles of Cu here equals 1 mole of O2. When we plug that in, we have 0.00936 moles of O2. So we're going to use this number now to plug it into this equation. So V equals N, which is 0.00936 moles. R, which is our constant, 0.0821 liters ATM, mole -1, and Kelvin -1. And it's important to have all these values because we're going to use these to cancel out every other value. And then we have temperature, which is, they give us 25 degrees Celsius, adding 273, we'll get Kelvin. So that gives us 298 degrees Kelvin. Over pressure, which they tell us here is 1.16 atm. So atm cancels out, Kelvin cancels out, and mole cancels out. And then we're just left with the liters. And once we plug that into the calculator, we get 0.197 liters of O2. And that's it.